Three-phase circuits. In this video, we are going to discuss about the relationship between line and phase values and the expression for power for a balanced star-connected load, and relationship between line and phase values and expression for power for balanced delta-connected load and different types of powers for three-phase load. Now, let us bring out the relationship between line and phase values and expression for power for a balanced star-connected load. So, balanced star-connected load in the sense we have taken a three-phase load which is of the same magnitude and they have a same phase angle and it is of same nature. Then we call such load as a balanced load and it is connected in the form of star connection. Now, look into the figure. So Z phase in all the three phases, if you observe, so the load is written as Z phase, Z phase, Z phase. So which means that we have considered a balanced load in all the three phases which have formed a star connection. Now, so we are giving a three-phase supply that is R by B. Now, let us analyze what are all the line voltages and phase voltages in this circuit diagram. So as I told you, line voltage is the voltage between the two line terminals. So what are the line voltages in this case? VRY. So VRY, VYB and VBR are the line voltages which are generally denoted as V suffix L. And what are the line currents here? Those are IR, IY and IP are the line currents and they are generally denoted as I suffix L. Similarly, the phase voltages. Phase voltage is nothing but the voltage across any load in a particular phase is known as phase voltage. So here voltage V or N is the phase voltage. Simply we can represent it as VR. Similarly, VYN which is called as VY and VBN which is called as VB. So therefore here VR, VY and VB are called as phase voltages. In general they are denoted as V phase, V suffix PH. Similarly, the currents passing through this load that is IR, IY and IB again. So these are the phase currents which are generally denoted as I phase. As already we have concluded that in star connection, I line is equal to I phase. So already we have brought the relationship between line current and phase current. Now let us find out the relationship between the line voltage and phase voltage. So how this line voltage and phase voltage are related together. So just see here from the figure we can write. So we have considered that V or Y. So these are all vectors. Okay. So this V or Y can be written as V or Y is nothing but it is the voltage between R and Y terminal. Now if you see here in the star connection, so V or Y is nothing but so this R terminal, this neutral and then this Y terminal. So we can write it as VRN plus VNY. So VRY can be represented as VRN plus VNY. Now this VNY can be represented as minus VYN. So if you change the direction, you can add a negative sign. Okay. So therefore, substituting this in the above equation, we get VRY is equal to VRN minus VYN. So this VRN, VYN and VBN, these are the phase voltages which can be generally represented as VR, VY and VB. So therefore, we write as VRY is equal to VR minus VY. Similarly, the other two line voltages are also represented in the same way. That is VYB is equal to VY minus VB and VBR is equal to VB minus VR. Now, let us draw the phasor diagram for this. So by taking the R phase voltage as the reference, so we are taking the phase voltages. So VR, which is considered as reference, and VY is lagging behind VR by 120 degrees and VB is lagging behind VR. Sorry, VB is lagging behind VY by 120 degrees. So therefore, the three phase voltages VR, VY and VB are represented which have a phase difference of 120 degrees between them. Now, let us find out what is the line voltage. So in the previous expression, let us consider the first expression, that is VRY is equal to, it can be expressed as VR minus VY. So that means VRY is nothing but it is a phasor sum of VR plus minus VY. That means phasor sum of VR vector plus negative VY vector. Okay. So how to get this negative vector? Where is this VR? So VR is already taken as positive and it is a positive vector. What about V minus Vy? How to get the minus Vy? So whatever first initially we have drawn, this Vr, Vy and Vb. So these are the assumed positive directions of the vectors. Now this is a positive direction of Vy. Then what is its negative direction? Negative direction of Vy, that is minus Vy vector will be in the opposite direction. So this is a representation of minus Vy vector. Now the phase difference or the phasor sum of this minus Vy and Vr will give you the line voltage, that is Vry. Now let us find out what is the magnitude of this line Vry. Now let us call some alphabets, that is the junction point is O and Vr vector is represented as OA and this line voltage OB is represented as OB. Now from point A, draw a perpendicular bisector on the vector OB. So perpendicular bisector will bisect the line OB exactly into two equal parts. So we can say that OC is equal to CB. Now if you observe here, this small OCB will form, OCA will form a small right angled triangle. So OCA will form a small right angle triangle. So in this right angle triangle, we need to find out what is the magnitude of OC. If we find out the magnitude of OC and double it, then we can get the total magnitude of OB vector, which is nothing but the line voltage. Okay. So to find out the magnitude of OC, if you consider this right angle triangle, so this angle is 30 degrees because if you take the resultant between these two vectors, that is Vr and minus Vy, if you the phase angle between this Vr and minus Vy will be 60 degrees, and if you draw the resultant between these two vectors, always the resultant will bisect the angle between these two vectors. Therefore, angle between Vr and Vl will be 30 degrees. Okay. Now, to find out this OC becomes the adjacent side for the angle 30 degrees. Therefore, the relation which gives the adjacent angle, the trigonometric function which is used to find out the adjacent side is cosine function. So let us use the cosine function, that is cos theta is equal to adjacent side by hypotenuse. So here in our case theta is 30 degrees. So therefore cos 30 degrees is equal to what is adjacent side? It is OC divided by hypotenuse is OA. So that is what written here. So cos 30 degrees. So in triangle OAB, in triangle OCB, this is a small triangle you need to consider. In triangle OCA, cos 30 degrees is equal to OC by OA. OC is nothing but adjacent side, OA is the hypotenuse. Then what is OC value? It is nothing but VL by 2. That is VRY by 2, which is nothing but VL by 2 divided by VR. So all this VR, VY and VB are the phase voltages. VRY, VYB and VBR are the line voltages. So let us represent this VRY as VL and VR as V phase. Also we know that cos 30 degrees is equal to root 3 by 2. In both this equation, this denominator 2 gets cancelled. Therefore, we get root 3 is equal to VL by V phase. Or we can also write it as VL is equal to root 3 V phase. Therefore, in star connection, what is the relation between line voltage and phase voltage? Your line voltage is equal to root 3 times of your phase voltage. Whereas line current is equal to phase current. So therefore, we can consider that always the line voltage is greater than that of phase voltage in case of star connection. Now, talking about the load, whichever we have considered in the previous circuit, we have taken Z phase. What type of load it is? How to find out this phase currents, phase voltages and all. See here, the load impedance. It may be lagging in nature or leading in nature. So it is lagging in nature if we consider the load is inductive. If we take a capacitive load, then the nature of the load is leading in nature. Okay. So if the load is inductive, then Z phase can be represented as R plus JXL, where R is the resistance, XL is the inductive reactance. And we can find out it in case of an inductive load, current, that is I phase, lags behind V phase by an angle phi, where phi can be given as tan inverse of XL by R. Similarly, if the load is capacitive, it is represented as Z phase is represented as R minus JXC, where R is the resistance and XC is the capacitive reactance. So in that case, the current, that is I phase, leads the phase voltage by an angle phi, where phi is given by minus tan inverse XC by R. Suppose if the load is a resistive load, then it will have only resistive part. The reactive part will be 0. Therefore, it is represented as R plus J0. And in this case, the phase current will be in phase with the phase voltage. And how to calculate this phase impedance? Z phase can be calculated as V phase by I phase. So this is the complete phasor diagram for a lagging power factor load. So here we can see that VR is represented, and this is VR, which is nothing but V phase, and this vector is I phase. Because we have considered a lagging power factor load for completing this phasor diagram. So because it is a lagging power factor load, your I phase lags V phase by angle phi. Similarly, the same thing holds good in the other two phases also. Now, let us see what is the expression for power. We know that single phase power is P is equal to VI cos phi generally. Because we are talking about the three phase. So when we talk about single phase, so we call it as per phase. So P phase is equal to, we represent it as V phase, I phase, cos phi. For balanced load, all the three phase powers are equal. Therefore, what is the total three phase power? Total three phase power P is equal to 3 into single phase power. Therefore, 3 into V phase, I phase, cos phi. We know that in star connection, V phase is equal to VL by root 3, whereas I phase is equal to IL. So representing that, we get, after simplification, we get the expression for total three phase power is root 3 VL IL cos phi. And whatever power we are representing here is the real power or average power. And hence the unit of this power is watts. Okay, so finally the three phase power in terms of line voltages and line current, we can represent it as P is equal to root 3 VL IL cos phi, whereas in terms of phase values, we represent it as P is equal to 3 V phase I phase cos phi. Next, relationship between line and phase values and expression for power for balanced delta connected load. So the derivation for this follow the same analysis as for the previous analysis which we did for the star connection. So here the same load, we have taken Z phase load which is connected now in delta connection, and this delta connected load is fed from a three phase supply which is shown in figure R by P. Again here VRY, VYB and VBR are the line voltages which are represented as VL, and IR, IY, IB are the line currents which are denoted by IL. Similarly, here VRY, VYB and VBR are the phase voltages which are denoted as V phase, and IRY, IYB and IBR are the phase currents which are denoted as I phase. Already we have concluded that in delta connection, line voltage is equal to phase voltage, that is VL is equal to V phase. So we need to bring out the relation between line current and phase current in delta connection. So for that analysis, let us apply KCL at node R. So if you observe the circuit, we have three nodes, that is node R, node Y and node B. Now let us consider node R. Let us apply KCL. So KCL says that the sum of the currents entering the node is equal to sum of the currents leaving the node. If you observe at node R, what are the currents entering the node? IR is a current entering the node, IBR is a current entering the node, and IRY is leaving the node. Therefore, we can write the equation as IR plus IBR is equal to IRY. This can be rewritten as IR is equal to IRY minus IBR. Similarly, we can write the same expressions, similar type of expressions at node Y and node B. So at node Y it is represented as IY is equal to IYB minus IRY, and at IB is equal to IBR minus IYB. Now, let us draw the phasor diagram by considering the first equation. So the equation we consider is IR is equal to IRY minus IBR. Now let us see how to draw the phasor diagram. So in this case, we draw the phasor diagram by considering the phase currents. So here we have taken the IRY. IRY is the reference vector which is nothing but a phase current, and I by B is lagging behind IRY by 120 degrees, and IBR is lagging behind IY by B 120 degrees. So these are the assumed positive directions of the phase currents. Now, the first equation represents IR is a phasor sum of IRY plus minus IBR. So you have an IRY, this is the IRY vector, and this is IBR vector. So we require the negative vector of IBR. So the negative vector of IBR will be obtained in the opposite direction. This is minus IBR. If we take the phasor sum of IRY and IBR, we get the line current, that is IR. So the same analysis follows. We call this as OA. I phase current is represented as OA and the line current is represented as OB. From point A, draw a perpendicular bisector on OB which touches OB at point C. Perpendicular bisector in the sense it cuts the vector OB into two equal parts. That means OC is equal to CB. Now, as I told you, this resultant vector bisects the angle between OA and that is IRY vector and minus IBR vector. So therefore the angle here is 30 degrees. Now if you consider the triangle OCA, so here we need to find out what is the value of OC which forms the adjacent side of the angle. So therefore let us consider cos 30 is equal to adjacent side that is OC divided by hypotenuse that is OA. So cos 30 is equal to, see here the equation, cos 30 is equal to OC by OA. OC is nothing but it is IR by 2 divided by OA is IRY. Also we know that cos 30 is root 3 by 2, that is IL by 2 by I phase. So here denominators 2 gets cancelled. Therefore we get the relation for line current and phase current as IL is equal to root 3 I phase in case of delta connection. So therefore here we can conclude that IL is equal to root 3 I phase and BL is equal to B phase. These are the relationship between line and phase values in delta connection. Similarly, the same. So if we consider that the load is of inductive in nature, it is represented as R plus JXL. Therefore, current lags the voltage. And if the load is of capacitive in nature, Z phase is equal to R minus JXC and current leads the voltage. If Z phase is resistive in nature, then it is represented as just R. Therefore, current is in phase with the voltage. So here also we can calculate Z phase is equal to V phase by I phase. And so this is a phasor diagram by considering a lagging power factor load. So we have drawn the phasor diagram by taking the phase current. See, in delta connection, both phase voltage and phase current both are equal. So anything we can take. And so this is the representation of the phase voltage, and your phase current is lagging the phase voltage by an angle phi if we consider a inductive load. So the complete phasor diagram is drawn for a inductive load. Now similarly the expression for power in case of delta connection also the three phase power is represented as P is equal to root 3 VL IL cos phi in terms of line voltage and line currents, or we can also represent it as P is equal to 3 V phase I phase cos phi in terms of phase voltages and phase currents. Now, let us consider the different types of power for a three-phase load. As already we have discussed in our single-phase circuits, there are three types of powers. What are they? Apparent power, active power, and reactive power. Coming to first active power. Active power is denoted as P, capital P. So it is known as a real power or average power or a useful power which is consumed in a circuit. And it is represented by the expression P is equal to root 3 VL cos phi and the unit is watts or kilowatts. Next one is reactive power. Reactive power is represented by capital Q. So reactive power is mainly due to the reactive component of current. It is not an useful power. We can also call it as a waste power. And it is given by the expression root 3 VL sin phi. The unit of this reactive power is volt ampere reactive, or simply we call it as watts or kilowatts. And the phasor sum of this active power and reactive power is called as apparent power. Therefore, for three-phase circuits, we represent apparent power as capital S, that is equal to root 3 VL. So, whose unit is given by volt amperes, that is VA or kVA. So finally, we can represent that S is equal to square root of P square plus Q square, which concludes that apparent power is the phasor sum of active power and reactive power. So these are the different types of powers for three-phase loads. Thank you.